example 2, chapter 15b. All right, this will be on entropy. All right. And as far as this is concerned, entropy is that we always have energy, heat always flows from hot to cold and not the other way around. That's one form of entropy. There's always a tendency to disorder, is what we mean here. Another example of that would be if I have a container, let's say I have gas here, of air, and this is a vacuum over here, and I have a slit separating them, and I open the slit. All right, as you might know what happened, the air is going to spread out due to pressure in here and eventually spread out so that it's equal, more or less equally spread out over the entire container. This is another form of entropy. It goes from order to disorder. We have it first, initially where it's all contained, and then we release it and it spreads out. Now theoretically, it's possible that all the gas could go back to one spot, to the other side again. That's possible, but it's so unlikely, you know, the odds are just astronomically small. This again, entropy is, we go from order to disorder. This part here where we have everything on this side is more ordered than when we open the slit and it spreads out. This is all forms of entropy. And then part of what it is, now this is a qualitative approach to this. We have this idea that it's, you know, it spreads out, we know that, and that's what we kind of know by entropy. How do we quantify that? And what we do here is in section 15.7, and so we define it as delta S is Q over T, where this is in joules and this is in degrees Kelvin. All right, so that's what we have there. So an example of this, if we have ice and we apply heat, so it turns into water. All right, the ice is more ordered than water because it's nice crystalline shape. Water is disordered, it's disorganized there. So what we could define it as is when we melt it, all right, say we have 1 kilogram of ice at 0 degrees Celsius, which is 273 degrees Kelvin. And we melt that ice, right? Now, to melt it is ml. Now, we did first part, LF is 80 kilocalories per kilogram. But we need this in terms of joules, and that is, in those units, it's 333 kilojoules per kilogram. Okay. All right, I had to get a calculator quick. And so what do we have here? All right, so what we're going to do is calculate the entropy for 1 kilogram. And so what we do, so we'll erase this. we'll then calculate Q. Q will be ML sub F, which would be 1 times 333 kilojoules per kilogram. So that's 333 kilojoules. Okay. Or, yeah. Okay. Now, the temperature is 273 degrees Kelvin. So delta S would be 333 kilojoules over 273, which is approximately 1.22 kilojoules per degree Kelvin. So that is the entropy of melting the ice to water. Now in this case, it's kind of easy because we're doing it at a phase change, so the temperature is 273 degrees Kelvin. All right, now we don't always have that happening. All right, what happens if we have entropy of mixing, say warm water and hot water, warm water and cold water? Now we know in that case, hot water is going to get colder, the cold water is going to get warmer, and they're going to mix together. So there's going to be more disorder of that. Instead of two separate hot and cold, we're going to have one medium temperature. Right? So there's going to be an increase in entropy. So how do we do that? Well, in that case, what we're going to do, and I'll leave it here. I'll leave this up for a minute, because I'll move on to the next part. And what we have here all right, we have M hot and M cold. Now let's have 50 grams of each. Okay. And this one is at 0 degrees Celsius, and say this one is at 6 degrees Celsius. All right, this is 273 degrees Kelvin, and this would be 333 degrees Kelvin. All right, so how do we do it? Mix them together. All right, you can calculate it, but since we have equal masses and 0, the temperature is going to be right in the middle. So we end up with 100 grams at the average of the two, which would be 303 degrees Kelvin. So we end up with 100 grams of water that's mixed together. So how do we calculate this change in entropy? Well, we're going to have entropy of, call this 1, the other 2, and what we're going to have is delta S will be delta S1 plus delta S2. Right? Now we can see here, as the temperature, as the object gets colder, the entropy goes down because it's moving slower, it becomes more ordered. So this one, the hot one, should actually become more ordered. The warm, cooler one should become more disordered. So this one should go down, that one should go up. So you might think, oh, the average, this one will go down, this will go up. and delta S should be 0. All right, so should delta S be 0? We'll find out it's not. Okay, so what we're going to do here in this case is use Q would be MC delta T. And I'm going to erase this part because I need that space. Well, I'll get this in a minute. Let me put down this. So this is 1, this is 2. So Q1 will be 0.05 times 1. Oh, not 1. We've got to do specific heat. 41. Now let's just do it in terms of grams. So that'd be 50 grams times 4,186 joules per kilogram times change in temperature of 30. Okay. So Q1, and it turns out Q2 is going to be the same. Q1 will be 50 6.28 times 10 to the 6th joules, right. Yep. And Q2 will be 6.28 times 10 to the 6th joules. Okay. So, except in this case, this one will gain heat, this one will lose heat. So that's going to be minus in that case. All right. So this is gaining heat, this is losing heat. So then that heat loss is 0. All right. Which is what we would expect. All right, so I'm going to go here now. And calculate QS delta S1 will be Q1 over delta over T. And what do we figure out for T? Now, technically, this should be like an integral. But we're not going to do that. So what we're going to do is take the average temperature. T is average. So if we're going from 273 to 303, the average of that is 288 degrees Kelvin. Up 50, yep. And for T2 average, it's going from 333 down to 303. So the average of that is 318 degrees Kelvin. Okay. So the average of the hot one going down is that. The average of the cold one getting warmer is that. So delta S1. So delta S will be delta S1 plus delta S2. All right. So delta S1 is the cold one getting warmer. So that will be Q1 over T1 average This will be Q2 over T2 average. So that'll be 6.28 times 10 to the minus 10 to the 6th over T1, which is 288, plus, this is going down, so that's minus 6.28 times 10 to the 6th over 318. We'll calculate that now. So 6.28 is 2.18 times 10 to the 4th joules per kilogram. Oh, joules per degree Kelvin. And this one minus 1.97 times 10 to the 4th. Okay. And we see that this is bigger, so the total entropy for this system is is 2.1 times 10 to the 3rd joules per degree Kelvin, or 2.1 kilojoules per degree Kelvin. And we have a positive entropy there. So this is how we quantify it for a relatively simple system. So the cold water has an increase of entropy. The warm water getting colder has a decrease in entropy, but the entropy of the cold getting warm is greater than the warm getting colder, and so we end up with a positive. So this is how we calculate it. Again, based on the fact we use delta T. T is going to be average in this case, of going from the cold up to the mixing temperature and the warm down to the mixing temperature, right? So that is entropy quantified, and this is what we always expect. The total entropy for a system always increases. All right? This is what we always see in any closed system. Now, some people say, well, the Earth violates that, but the question, we're not an isolated system. We are part of the sun, and the sun is becoming more disordered as it burns hydrogen and helium. So that's a case there where the closed system is basically the entire solar system. So that is it there. We're not going to cover any more of the section there. There are some interesting things about entropy and second law. That's like the last part of there talks about like the odds of when you flip a coin 100 times, on average, it'll be 50 of the other. If you do it enough times, you'll have 50 heads, 50 tails. Now it's possible you can have 100 tails in a row, 100 heads in a row, but much like what we had earlier, the idea of, a gas going all back to its original location is extremely remote. So that's chapter 15, and that's the end of heat and energy. Next chapter we'll be moving